So we're going to shift back now to talking about equivalence classes. So remember, according to theorem 9.14, congruence modulo 3 is an equivalence relation. You showed this on worksheet 5. So now that we know that congruence modulo 3 is an equivalence relation, we can talk about the equivalence classes. So what I want us to do now is determine the distinct equivalence classes in this case. So we need to start by selecting an integer. So select an integer. We're going to pick 0. So now we're going to look at the equivalence class for 0. So the equivalence class of 0, again, this is all the elements in Z where x is related to 0, but here my relation is congruence modulo 3, x is congruent to 0 mod 3, and this means that that 3 divides x minus 0, or just 3 divides x. So what are some elements in this set? Well, 0, 3 divides 0, 3 divides 3, positive 3 or negative 3, plus or minus 6, plus or minus 9. So they're all multiples of 3. And again, we know that there must be at least one equivalence class distinct from 0, from the equivalence class of 0. And that's because the equivalence class of 0, if I look at it, it doesn't contain every integer. So I need to pick an integer that's not in this equivalence class. So pick 1, for example. 1 is not in this equivalence class. And look at the equivalence class of 1. So the equivalence class of 1 will be all the elements in Z where x is related to 1. So this is all the elements in Z where x is congruent to 1 mod 3. This means that I'm looking for the elements in Z where 3 divides x minus 1. So you have a lot of numbers here. There's an infinite number, but if x is 1, 3 will divide 0. If x is 4, you'll have 3 divides 3, 7, so forth, going up. And then you also have negative numbers like negative 2, negative 5, negative 8. And if I look here, I can say again, there's another distinct, there's at least another distinct equivalence class, because these two equivalence classes that I have here, if I look, they don't contain every single integer. So for example, 2 is not in either one of these. 2 is not in the equivalence class of 0, and 2 is not in the equivalence class of 1. So I can now look at the equivalence class of 2. This is all the elements in Z where x is related to 2. So all the elements in Z where x is congruent to 2 mod 3. X in Z where 3 divides x minus 2. And so now let's write out what some of these elements are. Well, 2, if x is 2, then 3 divides 0. If x is 5, 3 divides 3, 8, 11, so forth. And we also have negative numbers going down, so -1, -4, -7, going down. So if I look at these 3 equivalence classes that I've found so far, the equivalence class of 0, 1, and 2, you'll see that these 3 contain every single integer in them. So I'll say here, every integer belongs to exactly one of these equivalence classes. One of these equivalence classes. So we found all of our distinct equivalence classes. There are 3 distinct equivalence classes. And those 3 distinct equivalence classes were the equivalence class of 0, of 1, and of 2. So there are my 3 distinct equivalence classes. Now what I want us to do is look at these equivalence classes a little bit closer and see kind of what's going on here. So I'm going to write out some of their elements so that we can compare these. So this one had 1, 4, 7, -2, -5. This one had -4, -1, 2, 5, 8, 11. So if we look here and think about this first one, these were all multiples of 3. So when I divide any of those numbers by 3, the remainder will be 0. If I divide 4, 7, 1 by 3, any of these numbers, the remainder will be 1. Remainder will be 1. And then if I look over here at any of the numbers 5, 8, 11, 2, any of these numbers over here, when I divide by 3, my remainder will be 2. So in the end, the equivalence classes correspond to our remainder when dividing by 3.